All right, optimization problems. First of all, you have to define the function that you're trying to optimize, okay? So if we take this picture here, let's see if we can figure out what that function is. Area is 30 square meters. Everything else is in the picture. What dimensions of the garden minimize the combined area of the garden and the borders? Well, first of all, I got to think about what they're asking there. What dimensions of the garden minimize the combined area of the garden and the borders? All right. So this area is the flower garden, and that is 30 square meters. What is the dimensions of the garden, combined area of the garden and the borders?
Would it be like 2x?
Well,
plus like 1y, or
let's put some variables on here. Let's make the length x and the width of that garden y. Okay, so the one thing we know is that xy is equal to 30. That's not the function we want to optimize. What is the dimensions of the combined garden and borders? What's the width in terms of x?
would it be just x plus 2?
Yeah, well, not 2. There's 2 over here also.
Oh, so it'd be x plus 4.
X plus 4 is the width of the garden. What's the height or the width of the whole area? And the height of the whole area is what?
Y plus 2.
So there is the area, or let's call it the combined area. And that is what we want to make a minimum, which is you're not always maximizing stuff, you're optimizing it, okay? Sometimes optimizing means minimizing it. I don't know why they would necessarily want to minimize it, but doesn't matter. We can do either one. Now, here's the key equation to be optimized. The problem is that's a function of 2 variables. I can't take the derivative of CA because I got 2 variables on the other side. But this gives me a way of expressing one variable in terms of another. If I solve this other equation for x, I get x equals 30 divided by y. Now, if I go into my combined area and substitute 30 divided by y wherever I see x, then I get 30 divided by y plus 4 times y plus 2. That is completely a function of y. Now my goal is to take the derivative of CA, set it equal to 0, because I know that's where minimums and maximums occur. solve it and come up with the proper value for y. Once we know what y is, then we'll easily be able to come up with x, because we know x times y is 30. Now, taking the derivative of this function. Now let's rewrite it. Hold on a second. Let me I'm going to just start writing smaller. So if I rewrite this thing so that I can use the power rule or in the product rule, then it's 30y to the minus 1 plus 4 times y plus 2. And I guess we could do that multiplication, FOIL it, get one polynomial. It might be easier to take the derivative. Let's try that. FOIL those together. I mean, I'll leave it up to you. Would you rather use the product rule, or would you rather multiply these two together, come up with the resultant polynomial, and then you'll only need the power rule?
I'd probably just multiply them together.
Okay. What's the first term? What's that times that?
So it'd be 30y to the negative 1.
Add the exponents.
Oh, so just be 30.
Okay. And that times that is plus 60 y to the minus 1. The middle term is plus 4y, and the final term is plus 8. I certainly can combine that with that. You with me?
Mm-hmm.
Now take the derivative of that, which is relatively easy. If that is CA, then what is CA prime?
So it would be
Term by term.
So 38 goes to 0, so that doesn't mean anything.
Okay.
Then you have negative 60 y squared.
Y to the minus 2.
Yeah. Negative, yeah. Plus 4. And that's it.
That's it. Okay. So let me see. Minus 60y to the negative 2 plus 4. Minus 60. Oops, hold on. Minus 60y to the negative 2 plus 4. That is CA prime. What are we going to do now? We've got the derivative of the function that we're interested in, and that we want to minimize. What am I going to set it equal to? Whenever you're optimizing, here's what you're looking for. If I have a function like that, I'm looking for these points. What are those? That's a local maximum, that's a local minimum, that's a local maximum. Those are the points I want to find. What is true about the first derivative at all three of those points?
That's equal to 0.
Okay, then that's what we have to do, is set this thing equal to 0. Whatever the function looks like, and we don't necessarily need to draw it, we know that the minimum is going to occur when the derivative is 0. So I'm going to write this in a little bit easier way to solve algebraically. Well, first thing I'm going to do is take the 4 over there. Next thing, I'm going to multiply both sides by y squared.
And then divide the sides by negative 4.
So I get y squared equals 15, which means y is equal to plus or minus the square root of 15. And there are two answers there, and almost certainly one of them is a negative, a minimum, and one of them is a maximum. They want the minimum, so we have to figure out which. Now, actually, there's only one answer that even makes sense.
Yeah, because you can't have a negative dimension.
You have a negative for y. So that is the only place where the function, the derivative function, is equal to 0. So how are we going to tell if that's a minimum? Y equals square root of 15, as opposed to a maximum. What if that's a maximum? In other words, a lot of times they're trying to maximize the area. For some reason, they're trying to minimize that entire area, which I find a little puzzling, because usually when you minimize an area, I guess given the area of the garden is fixed, it's 30 square meters, then maybe their question makes sense. So y equals square root of 15. Have any idea on how to figure out if that's a minimum or a maximum?
Would you find inflection points? No.
We take the second derivative.
Chart.
Let's take the second derivative of that function, plug in square root of 15, and if it's positive, it opens concave up. That makes it a minimum. If it's negative, it's concave down, makes it a maximum. Relatively easy to take the second derivative, since it's, there's no product rule or anything. Second derivative is 120 y to the minus 3.
So it's positive. So that means it is a minimum.
Correct. It's positive, concave up. And what dimensions of the garden? Well, y is square root of 15, which means x times y has to equal 30. So x is going to be 30 divided by the square root of 15. When I rationalize that, what do I get? 30 square root of 15 over 15. That now becomes 2 root 15. That's the dimensions of the garden. 2 root 15 by root 15, and that will give you a minimum area. I guess you might want to minimize that. Yeah, maybe you're putting this whole thing on a tennis court, and I want it as small as possible with the maximum size flower garden. Well, I've fixed my flower garden at 30 square meters, so now I got to figure out how to design the garden so that the entire area is as small as it can be given these other constraints. That has to be 2, that has to be 1, and that has to be 30 square meters. All right, this illustrates pretty good an optimization problem. On almost all optimization problems, you have two independent formulas. One of them is a function of two variables, and you use the other equation to make the function you're trying to optimize a function of one variable only. Okay. Which ones do you have to do? The odd ones? All of them?
Oh no, I just put those up for like reference because like I didn't really know how to do it all together.
Okay. I've actually got a pretty good one, if you don't mind, that
No.
I like a
No,
lot, and I think it's fairly instructive. Let me put it up this way, though. You have a parabola. The equation of that parabola is y equals 3 minus x squared. Okay? Question is what is the maximum size rectangle that will fit under that parabola? And when I say maximum, I mean maximum area. Notice I could draw the rectangle like that, or I could draw it like that. Which one's the bigger area? Or I could draw it like that, this. In other words, there's all kinds of ways to draw that rectangle. So the question is what are the dimensions of the rectangle in order to maximize it?
the dimensions?
In other words, I need to come up with the dimensions of this rectangle. Is it the box-like rectangle, or is it the longer rectangle, or is it the really long rectangle? Or is it something in between?
I don't even know how you'd come up with the dimensions to begin with.
Well, I'll go through it with you. This requires calculus. You could not solve this problem without calculus. Okay? Here's the way I'm going to do it. I'm going to call that dimension right there x. Makes sense since that's the x-axis. That's the y-axis. So whatever dimension I come up with is going to be x. Okay? What's the height?
Y?
Yep, exactly. So the area of the rectangle is 2x times y. You see why it's 2x?
No.
Because the base of that rectangle goes over to minus x.
Oh, yeah, that makes sense.
That point right there is x, and so the entire base of the rectangle is 2x.
Okay, that makes sense.
So the area is 2x times y. Well, here's what I want to optimize. I want to maximize that area. The way I'm going to do it is to take the derivative and set it equal to 0. And that's going to tell me the exact dimension of x that gives me the biggest box inside that parabola. Now, I cannot take the derivative as long as there's two variables on the right side of that equation. So we have this other equation here that tells me what y is as a function of x. So I substitute it. And now I've got the area of the box is 2x times 3 minus x squared.
Do you want to find a substitute for the x in that equation too?
No, I want it to have one variable. Watch. If I couldn't substitute for the x. I mean, I don't want to turn it back into two variables. I want to turn it into a function of one variable.
Okay.
I either have to substitute. Oh, did you ask, could I substitute for the x? Yes. But in this case, it's a little easier to substitute for the y. Notice that if I solve for the x, I'm going to have a plus or minus value. Don't want to have to deal with that. So I solve for the y, substitute for the y. Now I distribute. I get that. That's my area function. Now what?
Derivative.
Okay. What's a prime equal to?
6 minus 6x squared.
Now what?
Set equal to 0.
Okay. Now I get 6x squared equals 6. X squared equals 1. X equals plus or minus 1.
Can it only be positive again?
No. In this case, notice that x goes in the positive direction and it also goes in the negative direction.
Mm-hmm.
So the plus or minus 1 here really makes a lot of sense. In other words, that's the minus x, that's the plus x, and they come at 1 and minus 1.
Okay, that makes sense. Okay. Yeah.
So the dimensions of the box are 2 by 2.
Mm-hmm.
If x is 1, then this length here is a total of 2. And if I plug in 1 for x up here, I get a y is also 2. And so that's also 2.
So it's a square.
Uh-huh. Which shouldn't surprise one, that a square would be the shape that would give you the maximum area.
Makes sense to me.
For some reason, I remember solving this problem in the past. It seemed like I got plus or minus square root of 3 somewhere. But I don't know. I can't see any problem with my math here. Let me give you another one. These are a little tougher than your optimization problems that we're probably looking at on that page. Maybe, maybe not, but I'm trying to illustrate something here that is really important to grasp. And it's not easy to grasp. That is the first segment of a sine wave. Okay? Now we're going to take the same problem and say, what is the maximum rectangle that'll fit under that sine wave? Well, the equation of that sine wave is y equals sine x. Now, if I let that be x, now excuse me, hold on a second, I got to remember how to do this. I don't think I want that to be x. Yeah, I do think I want that to be x. The length of that rectangle is going to be x.
Yeah, and then the height is y. Because it's a box still.
Right. So the area is x times y, which is sine x, so it's x times sine x. I take the derivative of that. For some reason, I can't think of the problem that I'm trying to think of. I keep coming up with boxes here. If I make that dimension x, that point, then this is pi. So I would have pi minus x is this dimension. And since it's symmetrical, that would also be pi minus x. Let me just follow through on this logic for a moment. In other words, that dimension is pi minus x, right? It's easy enough to see. Which makes the width of my box the distance between x. No, that's not pi minus x. That's the width. That's not that point. See, I don't think I want the width of that box to be x. I think I want that point to be x, because that's what we're solving for, is where is that point going to come from? If that is x, what is this point right here? Well, pi minus x is the width of this. Pi minus x. But what's the width of my box? The width of my box is going to be pi minus that width, which is pi minus x, minus this width over here, which is another pi minus x. What does that give you? That gives you, if I take away all the parentheses, I got pi minus pi plus x minus pi plus x. And that cancels with that, and I end up with 2x minus pi is the width of that box. I think that's the right way to do it. And the height is y. And so the area of the box, if that's what I'm trying to manufacture, which starts out being 2x minus pi times y, now becomes 2x minus pi times sine of x. Take the derivative of that, set it equal to 0, and I'll find out what the coordinates of that point are. Now, you're bound to ask the question, why wouldn't I just make the width of the box x? Seems like it'd be a lot easier to solve.
Yeah, I'm a little confused by that.
I'm sure you are, especially since I started out that way. The concept I'm really trying to prove or demonstrate with this problem and the previous problem is that x is not a dimension. X is the point on the x-axis where I'm going to draw the right side of that box. So it's not really proper to label the width of the box x. It's not just a variable. In other words, this is the x-axis, that's the y-axis. So if I'm going to label something x, it has to be a point on the x-axis. And then once I've labeled that x, then I can figure out the width of the box based on all these other things. The width of the box is actually 2x minus pi. And so when you do all the math, it does not come out to be a square box. That is, actually the product rule probably works best here. Notice I'm going to have to use the product rule regardless, even if I distribute it. My first term is going to be 2x times sine x. Going to need the product rule. So I might as well use it to begin with because it's easier. So my answer for the derivative is 2x minus pi times cosine of x plus 2 sine x. It's quite easy to take the derivative. Now, setting this equal to 0 and solving it, not easy to do. you kind of need a calculator to do it. The reason is I have a combination of a polynomial and a trig function. Well, I don't know how to solve that. If I told you 2x is equal to cosine x, no clue. The only way to solve it is to graph both of them, and where they intersect is the solution.
Mm-hmm.
And that's how I would solve that one. I wouldn't be able to do it algebraically.
Okay.
I would have to graph, put one on the other side of the equation, graph both of them, where they intersect is my solution. But it's not a square box in this case. And in fact, no, I did the other one proper. I made x be the point. Yeah, no, I did the other one proper. My only mistake was when I started this one calling the width of the box x. Can't do that, because it isn't. X is a point on the x-axis. All right, let's have a look at some of your others on this page. Now that we kind of have an idea.
Uh-huh.
Let's do 28.
Covering a marble. Okay, imagine
a flat-bottomed cylindrical pot with a circular cross section of radius 4. All right. Hold on. Let me draw that. Close enough. You get the idea, right? It's a cylindrical pot. I guess what we're looking at here is it from the bottom. Okay. What is the radius? Ooh, hold on a second. I missed something when I read this question the first time. Imagine a flat bottom with a circular cross-section of radius 4. A marble with radius between 0 and 4 is placed in the bottom of the pot. What's the radius of the marble that requires the most water to cover it completely? Okay. Wish I could draw a little bit better. Let me try this. Here's our cylindrical pot.
Mm-hmm.
Here's the marble in the middle of that thing. Okay. We know this radius is 4.
Mm-hmm. And the marble between 0 and 4 too, right?
Yeah, the marble is 0 to 4. It doesn't tell us the height of this thing.
Well, it's a marble, so it should just have the same radius on it.
The marble does, but it doesn't tell me the height of the cylindrical pot, and it seems to me that that would matter, but I guess they're saying that it's at least 4 inches high. In other words, that is at least 4.
I feel like that's probably just not an important variable in the equation.
Yeah, I think that it doesn't, well, it probably doesn't matter if it's 4, 5, or 6.
Yeah.
But I would think that it might matter if it was only 2 or 3.
Yeah.
And our equations are going to require, I think, I don't know, let's lay out the equation. So what's the radius of the marble that requires the most water to cover it completely? Well, there answers our question. In other words, if the marble radius is 4 inches, then the height of this thing's got to be 4 inches.
Mm-hmm.
If the marble radius is only 2 inches, then the height of the water can be only 2 inches. But to cover the marble completely, so we're minimizing the amount of water, or maximizing the amount of water.
Mm-hmm.
So we need the volume of that cylinder.
So
The volume of a cylinder.
pi r squared times height.
Minus the volume of the marble. It's the volume of the marble.
I don't know what. Isn't it like 4/3 pi r cubed?
Uh-huh. Only this is a different r. We're going to call that r sub n. This r over here isn't even a variable. I can fill that in. It's pi times 16 h. And I know h is the same as this r, right?
Wait, what?
The height of the cylinder, or the volume of the water required to cover the marble, has to have a height of the same, 2r. To cover the marble, it has to actually be twice the radius of the marble.
Oh, yeah.
That's the volume of the marble, where the radius is just this distance. So if I want to cover the marble in water, I got to have a height of water that's at least twice the radius of the marble.
Mm-hmm.
So my volume of the water that is going to be required to cover that marble is 32 pi times r minus 4/3 pi r cubed,
Mm-hmm.
where r is the radius of the marble.
And do you still want it to be r sub m?
No, don't need it, because both these r's are the same now. In other words,
Oh,
what I originally called r was actually 4.
okay, yeah, that makes sense.
Not a variable. So I changed that r squared to 16, and the height of the water, not so much the right cylinder, but the water, is going to be 2 times the radius of that marble. So I make h be 2r. And now I have a volume of water required that is a function only of the radius of the marble.
Mm-hmm.
I can take the first derivative of it, I can set it equal to 0, and figure out the radius of the marble that maximizes the volume of the water.
Okay, that makes sense, yeah.
And this one's not that hard to do either.
Yeah, like when you have that down, then it gets really easy.
Well,
so
yeah,
this was 32 pi.
Quickly, 32
what?
pi minus 4 pi r squared,
Yeah.
which means 4 pi r squared equals 32 pi. Pi's cancel. 8 equals r squared. R equals 2 root 2, positive only. Okay. I'm thinking about that for a second. They want the radius of the marble that requires the most water to cover it completely. Ah. What my first thought was is, well, if I make the radius of the marble bigger, won't I need more water? I'll certainly need higher water, right?
Mm.
In other words, 2 times root 2 is about 2.8. Okay? So they're saying a radius of 2.8 of the marble requires the most amount of water to cover it. Well, what if I made the radius 5? That means I got to have higher water. But it also means less water, because now I need less water around here.
Mm-hmm.
So increasing the radius of the marble doesn't necessarily increase the amount of water needed to cover it. Imagine if I made the radius of the marble the same as the radius of the cylinder. Let's make it 4. Well, then the marble sits end to end and there's hardly any way to cover it. Even if I have a cylindrical pot that's big, that's 8 meters high, that doesn't require much water to cover that marble. So the size of the marble isn't clear as to whether making it smaller or bigger increases or decreases the amount of water to cover it. So this is kind of a cool calculus problem also that can only be solved with calculus. And you get a rather strange answer, 2 root 2. In other words, you don't get 1, 2, or 3, or 4. You get an irrational number.
Mm-hmm.
But again, we had 2 equations. Our most important equation was the volume of the water that's going to be in this pot. And that is the volume of the pot minus the volume of the marble. That's the amount of water that's going to be in there if it's up to the top. I should say the height of the water. Okay? And our second equation is H is equal to 2 times the radius of the marble. That has to be true because we're barely covering the marble. So the water has to go up a full diameter of the marble, which is 2 radiuses. Now I can substitute 2r for h and end up with a volume function that is a function of r only, the radius of the marble. Now it's not completely clear to me whether that answer we got would be a minimum or maximum. Who's to say that's not the minimum amount of water that would require to cover the marble? Well, that's easy enough answered by taking the second derivative again. Second derivative, that goes away. I got minus 8 pi r. And if I stick a positive r in there, I have a negative. That means it opens down. That means it is a maximum. That creates the maximum value of this function. If I were to take this function and graph it on Wolfram alpha, whatever it looks like, this cubic function here, we're going to be looking at the maximum at 2 root 2 on the r-axis, because the second derivative is negative. And for a problem like this, that's kind of important because I don't know that I'd have been able to guess. If you increase the size of the marble, do you increase the amount of water that needs covering it, or do you decrease it? And it depends. It's a function of that radius of that marble. And obviously, if I make the radius smaller than 2 root 2, I don't require as much water to cover it. And if I make it bigger than 2 root 2, I don't require as much water to cover it. The most amount of water required to cover it is when the radius of the marble is exactly 2 root 2.
Mm-hmm.
See if we can find one that...
Wait, can we do mean value theorem now?
Sure. Do you have a problem, or you just want to talk about the mean value theorem?
I don't really get the concept, and I took some pictures of the problems earlier.
Well, we don't have much time. I think I can explain it. Take a continuous function. It's differentiable at all points.
Mm-hmm.
The mean value theorem says that whatever the average slope is between points A and B, and if I want to figure that out, slope of that line right there, right? In other words, this is f of B, this is f of A. Slope is the rise divided by the run. So the slope is f of B minus f of A divided by B minus A. Okay? What the mean value theorem says is that as long as this function is continuous, there has to be some point on the function whose slope of the tangent line is that same. It's impossible for there not to be a spot on the function that doesn't match that slope.
That secant slope?
Yes.
And how do we go about finding that?
Well, the slope of the secant is that, and the slope of the tangent line is the first derivative of that function evaluated at wherever that point is. And we will be able to solve for that point based on knowing the slope of the secant line.
Mm-hmm.
Can you give me one problem and we'll do it?
Oh, yeah, I have some in the book. I took a picture of it.
Okay, go ahead and send it to me real quick.
It's there.
Okay, which one is it?
Second picture, I think.
That's exactly what that thing says.
Mm-hmm.
The f of b minus f of a over b minus a, that's the average slope of the secant, that's the slope of the secant line. And this says that that's equal to the derivative of the function at some point C. There has to be a point C that matches that average slope. And then a little algebra turns it into this. So, where is a problem? All right, let's do one of these problems like 7. Determine whether Raleigh's theorem, that's the mean value theorem, applies to the following functions on that interval. If so, find the points that are guaranteed to exist by Raleigh's theorem. Now, here's just a little funny aside. Raleigh was a famous mathematician who never accepted the validity of calculus his entire life. He thought it was not correct.
Wait, really?
Uh-huh. And yet they name a theorem after him. I've always thought that that's humorous. So
yeah.
if we look at 7, Well, we know we have to take the derivative. Whoops, hold on. So f prime of x is equal to I'm going to multiply this out. That's x squared minus 2x plus 1. So that's x cubed minus 2x squared plus x. I think. Let's see. That's x squared minus 2x plus 1 all times x. It's x cubed minus 2x squared plus x. Okay. So that's the function. The derivative of the function is 3x squared minus 4x plus 1. And what is the average slope between 0 and 1? Remember, it's f of b minus f of a all over b minus a. Well, what's f of 1 equal to?
So would it be...
And here you have to go back to the original function, not the derivative. In other words, we want the slope of that secant line between 0 and 1 on this function. So what's f of b?
F of b would be... would it be 1 minus 2 plus 1? So it'd just be 0.
Okay.
Minus...
What's f of a?
You're plugging in 0, so it'd be 0 minus 0.
Okay. So the average slope is 0. It's 0 divided by 1, but it's still 0. Okay? So we have to find where the derivative has a slope of 0. It's basically as simple as that. You're not always setting the derivative equal to 0, but they keep giving us problems where we have to set the derivative equal to 0. Usually what you have to do in these problems is set the derivative equal to whatever you got, that average slope. And it isn't always 0. That average slope doesn't have to be 0. It could be 2, it could be any number. But that's what I'm going to set the first derivative to, is whatever number I got. So I'm setting 3x squared minus 4x plus 1 equals 0. That factors into 3x minus 1 times x minus 1, which means x can be either 1 or x can be 1/3. At either spot, your tangent line is flat. Now, this function we were looking at is a cubic. So if I were to look at it like a typical cubics do that, and there's going to be 2 spots where the tangent line is 0. And we need both of them. What point is guaranteed to exist? Well, no, these are both between 0 and 1. Notice there's a bracket next to 1 and 0. So a number on the edge counts, I think. We got 5 minutes. I'm going to graph this in Wolfram Alpha, and let's see what this thing looks like.
Okay.
3x squared minus 4x plus 1. 3x squared minus 4x plus 1. I want to plot the original function, not the derivative. The original function was 2x cubed no, it's x cubed. It's x cubed minus 2x squared plus x. And you can see what the slope is between 0 and 1. Flat. Right? Here. In other words, our average slope between this point and this point, the rise is 0. Yeah, it's 0. So what the mean value theorem says is there has to be a point from there to there in that interval that also has a 0. You would not be able to draw a function and get from 0 to 1 without having this point right here.
Yeah, and that would just be a tangent slope. That would be 0 too then, right?
That's at 1/3.
Okay.
So the two answers we got, I got x equal 1 and x equals 1/3. Well, you can also see the tangent at 1 is also 0.
So those are just both applicable answers then?
The mean value theorem really has more to do with, is there a point between the 2 points? There has to be a point between the 2 points. 1 is not between them. It's on the end of it. So the answer is 1/3. 1/3 is guaranteed to exist by the mean value theorem. I'm not sure that 1 is. Maybe it is. Because the interval was 0 to 1, including 1. But I think in general, they're always looking for a point in between.
Okay.
Okay? In other words, if I have a weird looking function like that, and I can tell that the slope between there and there is that, the mean value theorem guarantees me that one of these tangent lines matches this slope, like that. That point has to exist. I would not be able to draw this function in a manner where I did not have at least one point whose slope was the same as that secant line, that average slope. And that's the mean value theorem in a nutshell. Usually these theorems, the mean value theorem and the intermediate value theorem, you don't have so much problems based on them as they're used as theorems to prove higher theorems. That's their main purpose. They're called existence theorems. We know a point exists. Now, it turns out that the mean value theorem actually has lots of good problems they can give you because they're all designed around this model, whereas you figure out the slope between the 2 points, and then you find where the first derivative is equal to that slope. And that's the way every one of them unfolds. So you can have some good problems for the mean value theorem. The intermediate value theorem, it's harder to have a good problem on that. That's the one that says you can't go from 20 miles an hour to 60 miles an hour without going through every speed in between. You can't go from 20 to 60 without going 32. You can't jump over 32. That's what the intermediate value theorem says. There are going to be, on a continuous function, there are going to be every known value between those two has to be on the curve. All right. Jake, I'm going to let you go. It's late. It's been a long day, I'm sure, for both of us.
Yeah. All right. Well, you have a good night, though.
Okay, you too. Talk to you next time.
Yep.